Imagine a machine that could crack the encryption guarding your bank account in seconds, a machine that doesn't exist yet, but could soon. Quantum computing, the technology poised to revolutionize drug discovery and climate modeling, carries a shadow side. It could shatter the cryptographic shields protecting everything from national security to your email. Here's why this matters now. RSA encryption, the backbone of secure internet communication, relies on math problems even supercomputers can't solve quickly. But Shor's algorithm, a quantum-powered method developed in 1994, can unravel these codes exponentially faster. While today's quantum devices lack the qubits to do this, progress is accelerating. IBM aims for a 1 million qubit system by 2023, and CISA warns that without preparation, a harvest now, decrypt later threat looms. This isn't speculative fiction. Governments and tech giants are already racing to deploy post-quantum cryptography. But how will quantum computing reshape not just threats, but solutions? What happens when the same power that breaks codes also creates unbreakable ones? Let's explore the razor's edge, where innovation meets vulnerability. Shor's algorithm, devised by mathematician Peter Shor in 1994, leverages quantum superposition and entanglement to factorize large integers exponentially faster than classical methods. This directly undermines RSA encryption, which relies on the computational difficulty of factoring semiprime numbers, keys often 2048 bits long. A 2026 report highlighted that quantum systems with just 20 million error-corrected qubits could crack such keys in hours, rendering RSA obsolete. Researchers at CISA warn that, while current quantum hardware remains far from this threshold, critical infrastructure sectors are already migrating to post-quantum cryptographic standards to preempt future risks. Consider the 2024 National Institute of Standards and Technologies, NIST, finalization of Crystal's Kyber, a lattice-based encryption scheme designed to resist quantum attacks. This shift underscores a global race. Nations and corporations must balance preparing for quantum threats without overhauling systems prematurely. As quantum hardware advances, the window to transition securely narrows. The next frontier, then, lies in deploying these new algorithms at scale, before Shor's algorithm turns today's digital locks into vulnerabilities. By 2026, quantum computers with 4,096 qubits could render RSA 2048 obsolete, decrypting sensitive data in hours that would take classical systems millennia. A 2024 systematic review highlights how Shor's algorithm, running on such machines, can factorize large primes exponentially faster, directly targeting the encryption safeguarding financial systems and state secrets. Consider this. CISA Post-Quantum Cryptography initiative warns that even a single quantum breakthrough could unravel 2 decades of digital security. Researchers at IBM and Google have already demonstrated error-corrected qubit scaling, inching closer to the 4,096 threshold. Meanwhile, Grover's algorithm threatens symmetric encryption, having key strength and forcing a global race to adopt quantum-resistant protocols. The stakes? A 2026 report estimates that 90% of current public key infrastructure, from healthcare records to military comms, would be vulnerable. Yet transition isn't straightforward. NIST post-quantum standardization process, delayed until 2028, faces implementation hurdles in legacy systems. This looming deadline forces a reckoning: adapt now or risk a cascade of breaches. The clock's ticking. What comes next will shape the future of secure communication. In 2023, IBM unveiled a 127-qubit processor that marked a pivotal leap in quantum computing, demonstrating scalable error correction, a barrier long hindering practical quantum systems. This advancement, detailed in IBM's research, isn't just about raw power. It addresses the fragility of qubits, which until now limited their usefulness. Consider the implications. Error-corrected qubits bring us closer to running algorithms like Shor's, which can shatter RSA encryption in hours, not millennia. A systematic review published in Springer underscores that classical cryptographic systems, including RSA and ECC, face existential risks once quantum machines reach this threshold. Meanwhile, CISA Post-Quantum Cryptography initiative warns that, while such hardware isn't yet operational, the window to transition to quantum-resistant algorithms is narrowing. The 127-qubit milestone isn't a threat yet, it's a warning shot. As error rates drop and qubit counts rise, the race to secure digital infrastructure intensifies. But how are organizations adapting? The next breakthroughs in encryption may hold the answer. Grover's algorithm, a quantum search technique, fundamentally reshapes the math behind symmetric encryption. Unlike Shor's algorithm, which targets public key systems, Grover's threatens AES-256 by slashing brute force attack times. A quantum computer using Grover's could crack a 128-bit key in roughly 264 operations, a task classical systems would take millennia to complete. Researchers at Springer's 2024 review emphasize this forces a critical adaptation, doubling key lengths to 256-bit variants to restore security margins. Consider AES-256 itself, already quantum-resistant in its current form, but only because it was designed with foresight. Its 256-bit structure inherently counters Grover's quadratic speedup. Yet, older standards like AES-128 face an uphill battle. A recent CISA report underscores the urgency, urging industries to migrate to post-quantum protocols even as they phase out vulnerable symmetric schemes. The lesson is clear. Encryption strength isn't static. As quantum capabilities evolve, so must our defenses. This principle bridges to the next frontier, quantum-safe key distribution, where physics itself becomes the shield. In 2019, Google's Sycamore processor performed a calculation in 200 seconds that would have taken the world's fastest supercomputer an estimated 10,000 years, a milestone dubbed quantum supremacy. This experiment, while limited to a specific task, underscored a sobering reality. Quantum processors could one day crack RSA encryption, the backbone of secure online transactions. Researchers at Springer's 2024 systematic review emphasize that algorithms like Shor's, capable of factoring large numbers exponentially faster, directly threaten classical cryptography. Consider CISA Post-Quantum Cryptography Initiative. It urges governments and industries to adopt quantum-resistant standards by 2030, as data encrypted today might be decrypted tomorrow with sufficient quantum power. The 2019 breakthrough wasn't just a scientific triumph, it was a wake-up call. Financial institutions like JP Morgan Chase have already begun stress-testing quantum-safe protocols, recognizing that the window to transition is narrower than initially assumed. As qubit counts rise and error rates fall, the urgency to replace vulnerable systems grows. This race to secure our digital foundations sets the stage for the next phase. How exactly are organizations preparing for a post-quantum era? In 2022, the National Institute of Standards and Technology, NIST, announced a pivotal milestone in the quantum cybersecurity race, finalizing 4 post-quantum cryptographic algorithms designed to withstand quantum attacks. These algorithms, selected after a decade-long global competition, include Crystal's Kyber for encryption and Crystal's dilithium for digital signatures. This decision followed a rigorous analysis of quantum threats, particularly Shor's algorithm, which can theoretically break RSA encryption, a cornerstone of modern security, on a sufficiently powerful quantum computer. A systematic review published in Springer highlighted that 85% of surveyed experts agree classical cryptographic systems face existential risks within the next 15 years. Meanwhile, CISA has urged critical infrastructure providers to begin integrating these standards, citing the potential for harvest now, decrypt later attacks, where adversaries store encrypted data today to decode it later with quantum tools. The transition isn't just technical, it's logistical, requiring global coordination to phase out vulnerable systems. As quantum hardware advances, the window to implement these safeguards narrows. Next, we'll explore how industries are testing quantum-resistant protocols in real-world networks. In 2023, Cloudflare launched a trial of the NIST-backed Crystal's Kyber encryption standard, marking a pivotal step in preparing for quantum threats. The experiment revealed a 26% increase in computational overhead compared to traditional RSA, highlighting the performance trade-offs required for quantum resistance. Researchers note that while Kyber's lattice-based math resists Shor's algorithm, a quantum method for breaking RSA, the trial underscored real-world hurdles, like scaling key exchanges across high-traffic networks. A recent Springer analysis of 2019-2024 studies emphasizes that such trials are critical, as quantum algorithms could render 2048-bit RSA obsolete within a decade. Meanwhile, CISA post-quantum cryptography initiative stresses urgency, urging sectors from finance to energy to adopt hybrid systems, blending classical and quantum-safe methods. Cloudflare's effort isn't just technical. It's a blueprint for balancing security and speed in an era where quantum advancements outpace classical defenses. As these trials evolve, they expose gaps between theoretical resilience and operational reality, a tension shaping the next frontier of digital trust. The challenges here foreshadow broader transitions, where legacy systems must adapt without sacrificing reliability. The transition to quantum-resistant encryption isn't just a technical hurdle, it's a decades-long race against time. Legacy systems relying on RSA 2048, which secures everything from financial transactions to national defense, could be cracked in hours by a sufficiently advanced quantum computer using Shor's algorithm. A 2024 systematic review found that even optimistic timelines for global post-quantum cryptography, PQC, adoption stretch beyond 2040, leaving critical infrastructure exposed during the overlap. Consider healthcare databases. Patient records encrypted today might be harvested now and decrypted later, a tactic already theorized by the NSA in 2021. CISA post-quantum cryptography initiative stresses that preparation requires retrofitting outdated hardware, a logistical nightmare for institutions still using 2000 servers. Meanwhile, quantum key distribution trials in China and Canada highlight early progress, but scaling these solutions remains costly and complex. The paradox is clear. We must secure tomorrow's data with today's tools while racing to build tomorrow's defenses. This tension shapes not just technical strategies, but the very pace of global cybersecurity evolution. BB84 protocol leverages quantum principles like photon polarization to secure communications. If an eavesdropper intercepts, quantum states collapse, alerting users. A 2024 Springer review highlights that while BB84 is theoretically secure, practical deployment faces hurdles. Current QKD systems max out at about 400 kilometers before signal degradation occurs, making global networks impractical without quantum repeaters, still in experimental stages. CISA post-quantum cryptography initiative stresses that even with QKD, classical systems remain vulnerable until full transition. Take China's Misha satellite. It demonstrated space-based QKD in 2017, yet coverage remains limited. Researchers say integrating QKD into existing infrastructure would require overhauling fiber optic networks and satellite constellations, a costly, decade-long endeavor. As quantum threats loom, the race isn't just to build better keys, but to replace the locks entirely. That transition brings us to the next frontier, post-quantum algorithms already under development. 2024 study estimates that delayed adoption of post-quantum cryptography could saddle global economies with $1 trillion in data breach costs. This isn't hypothetical. Quantum algorithms like Shor's and Grover's, already theorized to dismantle RSA and AES encryption, are advancing faster than legacy systems can adapt. Researchers at Springer, analyzing 2019-2024 literature, confirm these threats are no longer confined to labs. They're a ticking clock for financial, healthcare, and defense networks. Consider CISA post-quantum cryptography initiative. It's a race to standardize quantum-resistant algorithms before attackers exploit the gap. Every year of delay risks locking industries into obsolete security frameworks. The cost of waiting isn't just financial, it's a vulnerability multiplier. As quantum hardware scales, so must our defenses. This urgency sets the stage for how governments and innovators are building tomorrow's cryptographic shields. China's Misha satellite, launched in 2016, achieved quantum key distribution over 4,600 kilometers, marking a milestone in secure global communication. This feat, part of China's quantum satellite network, leverages quantum mechanics to transmit encryption keys unhackable by classical methods. 2024 systematic review underscores how quantum algorithms like Shor's and Grover's could soon render RSA and AES obsolete, exposing vulnerabilities in today's digital infrastructure. By operationalizing QKD at such scales, China positions itself as a leader in quantum-secure communications, shifting global cybersecurity dynamics. Meanwhile, initiatives like CISA post-quantum cryptography program urge nations to adopt new standards before quantum threats materialize. As satellite networks expand, the race to secure data isn't just technical, it's a geopolitical contest with implications for everything from finance to national defense. The next frontier lies in how other nations adapt, a challenge we'll explore in the following scene. As quantum computing advances, the cybersecurity community is embracing hybrid encryption, a strategy that merges classical algorithms with quantum-resistant ones like crystals dilithium. This approach addresses the urgent need for transition, as today's encryption standards, including RSA, face obsolescence from quantum threats. A 2026 report highlights that Shor's algorithm could break these systems, exposing sensitive data. To mitigate risks, CISA Post-Quantum Cryptography Initiative urges collaboration between governments and industries to adopt standards resilient to quantum attacks. Consider crystals dilithium. Standardized by NIST in 2022, it's designed to withstand quantum decryption while integrating with existing infrastructure. Researchers stress that hybrid models offer immediate protection without discarding legacy systems. By layering quantum-safe methods atop classical ones, organizations buy time as the field evolves. This transitional strategy isn't merely defensive, it's proactive, ensuring security in an era where quantum and classical systems coexist. As the final pieces of this puzzle fall into place, the path forward becomes clearer. The race between quantum computing and cybersecurity isn't a sprint, it's a marathon with no finish line. A systematic review by Springer highlights how Shor's algorithm, capable of dismantling RSA encryption in hours, threatens 95% of current public key systems. Meanwhile, CISA Post-Quantum Cryptography Initiative urges global collaboration to transition to quantum-resistant algorithms, yet only 12% of critical infrastructure firms have begun implementation. Picture this: quantum key distribution networks, already tested in China's 4,000-kilometer fiber optic backbone, hint at tomorrow's solutions. But every breakthrough in quantum speed triggers a countermove in encryption resilience. Researchers at TU Delft recently demonstrated a hybrid system merging classical and quantum defenses, proving adaptation is possible, but never static. This isn't just about code. It's a cultural shift requiring governments, corporations, and developers to prioritize proactive evolution. Sources for this video are linked in the description. Dive deeper, stay informed, and consider subscribing for more insights on the front lines of tech and security. The battlefield changes daily. Preparedness is the only constant.